Okay, this is a companion video to discussion of the addition of geometric constraints, 2D geometric constraints, in fact, in AutoCAD. I actually haven't exposed myself to 3D geometric constraints, but those, in fact, are what exists in Inventor, and you have to realize that 2D geometry is just a subset of 3D geometry. So I'm introducing you here to a program that is a 2D sketchpad called the Geometer Sketchpad. And, there'll be other links from here going back to the history of this term sketchpad, and I'll be looking into the history of this, if this in fact does come from 1962 in the parametric modeler and the object-oriented programming system that has the web all astir on YouTube, going back to 1962. So, this program is available for about $30 for students, and its target market goes all the way down to, I would presume, around 3rd grade, and all the way up through graduate school. Though once you get into higher order mathematical engines, most of the tools here we'll see a little arcane or a little bit outmoded, but they're pretty good. And once you jump through a few hoops, you can do some pretty amazing stuff. So what we're going to do here is I'm just going to do a real quick demo and see how geometric constraints might work in this program. So I'm going to right away click on grid, and I'm going to show the grid here, and I'll show you some of the things that the basics that you'll learn, that I've learned over the last 4 or 5 months since I came upon this last summer at the same time that a local high school math group discovered the same thing at the same time. And we'll talk about how one evaluates technology and the like, but if you've got a couple of different people coming at you with good reviews, that's one place you might pursue that particular technology or that software. So if you notice, what I've done here is I can kind of move around. I grab the first point, and that is the origin point, and this is kind of a scale point. So I'm kind of scaling this in or out so I can get it, all the way up where it's in the order of a mapping scale here, where we're showing this goes everywhere from 10,000 feet left and right, and 6,000 feet up and down. Now, I do want to point out that I'm going to continue with this demo, but the fact is that you do not want to get in the habit of drafting these things where they're not to the same scale. So that these boxes, in fact, are not gridded out correctly. 4 in this direction, 1, 2, 3, 4. 1, 2. Actually, they are. So visually, it's just my brain that doesn't see that this is actually at a scale of 1 to 1. All right, so those are a couple of things. The things that this originally is used for, I believe, in classrooms, is to basically go ahead and do things like drawing a circle and drawing a line to that circle, and then eventually constraining it. And if you look at here right now, once I've drafted that line, if I take this and I animate the point, it's going to drag that line around the circle. So it's constrained one point to this circle. All right, so that's kind of the first basic, and the part of this that really got me to be fascinated by it. And I'll post out a couple of videos that shows this particular software being used to model some linkages and mechanisms, which are a big part of mechanical engineering and all engineering, if you really think about how things are built. Well, amongst the things we can do now is we can actually put a point out here now, that point there, and now we can, like we often do, is we can select that, and now I'm holding the shift key and a left click again. I've selected that, and I can go to the construct here, and I can construct a I'm curious about that one. Circle center radius. That's not doing for me, because that's basically giving me something not that I want. I am going to go ahead and construct a perpendicular line. And once again, now I'm going to animate one point. and I'm going to turn it on. And what you notice now is that one constraint or one animated point with a constraint drives another constraint, and you can think about how basic mechanical design goes about. A series of linkages and mathematical connections that go between parts, constraints in 3 dimensions, x, y, and z, and then 3 rotations gets you your degrees of freedom. So if you think about this point here, it is locked, and we're only thinking 2D here, so we've got 4 degrees of freedom, I guess. I'm sorry, 1, 2, 3, 3 degrees of freedom about that point. In other words, it can't move up or down, it can't move left and right, but it is allowed to rotate. So those are the possibilities in this plane, because it's a two-dimensional plane. So I'm going to go ahead and stop this, and I'm going to add another one. I'm going to put a point out here. And now I can take this and I can highlight this and highlight that, and I can construct a parallel line. And once again, turn it on. Now if you notice, because that was the point that was highlighted, this is the one that is actually going through. So if I now instead grab this once again and animate it, you get that constraint. And so the concept of the fact that what's really occurring here is math, not necessarily graphics, you start to realize that the two things are one and the same. That's kind of what you learn in analytic geometry. So to show you finally that these are the same thing, I'm going to use one of the more important tools when you're using this with your kids or yourself, is to learn to tie the mathematics to the graphics. And even if it's not pure mastery, it's realizing that yes, these are the same things. And that's why a lot of great designs are just done by sketching, hand it over to someone else who goes through and works out the mathematics, the difference between conceptual design and engineering design. And so if we look at here, I'm going to grab this circle and I'm going to measure, I guess I can only grab one thing. I'm going to grab the circle here. I'm going to measure the equation, put the equation in, that's the equation of the circle. Huge, nice, cool, unbelievable. I'm also going to take that one now and measure the equation. And I'm going to take this one and I'm going to measure the, going to do only one at a time. You're kind of going to realize that when you get into some of these parametric modelers. If you grab too many things, you don't get a good choice. I'm going to measure the equation. And finally, I'm going to take this one and measure. Well, lets me do one. It won't let me measure the equation. Measure the slope. I'm just going to put the slope here. All right, now you're going to realize here, as I'm going to do right now, is I'm going to actually add one more parameter to this, and I am going to grab this here and I'm going to measure number. I'm going to calculate. I'm going to calculate 1 divided by, 1 divided by the slope parameter. Put it there. And what you're going to see here, as this rotates, you're going to see that we know that the perpendicular line to another line is the negative reciprocal. And you're going to see, if I can move this down here, you're going to see this number here and that number there being equal and opposite as we rotate this. So I'm going to once again go to here and turn it on. And if you stop at any one point, you realize, let's see if it keeps up. The equations of these lines are y equals mx plus b, and m is the slope. The equation of the slope of this line is that number, and the negative reciprocal of the slope is that number. And you realize that that is a lot of what's going on when you're doing drafting and engineering. You are constraining mathematics or constraining physicality. And all reality, a lot of the math that we do, in quotes, is trying to describe the physical world. Thanks for listening. That's a little discussion of constraints in Sketchpad.